In this second hour, or part of a second hour, we will talk about the paradigm of inference by conditioning. So conditioning as opposed to variable elimination. Conditioning is an interesting paradigm because, in fact, it came first. And let me tell you, there was an open problem with respect to this that lasted for almost 15 years. And the solution was fascinating, as you'll see. But here's how it goes. In the 80s, Pearl proposed the first algorithms for exact inference. We talked about the polytree algorithm, which was meant for polytrees. And then he wanted to do networks like this. This is not a polytree, right? Remember, polytrees are also called singly connected. They don't have loops. This is a multiply connected network. So what do I do? The polytree doesn't apply to it. So Yuda came up with this idea, which is the following. The idea is, suppose that those yellow nodes were observed. They're part of the evidence, right? And I want to do inference on that guy. You guys already know by now that I can prune a network before I do inference, correct? In this case, what can I do? I can delete the edges outgoing from observed nodes. That's one of the way we prune networks before inference, right? What happens if I do it here? Look how it looks. Suddenly it became polytree. Then I can run the polytree algorithm on it. You guys see that? Okay, so now here I got lucky. The evidence allowed me to prune the network so I can move it from a multiply connected to singly connected. What if I don't have that evidence? The idea is try all possible combinations for these yellow nodes. Right? So 1, 2, 3, 4 in this case. If they're binary, that's 16 different combinations. For every one of these combinations, I pretend it was evidence, I compute, and now what do I do with the 16 numbers I get? I add them up. That's basically this algorithm that's called cut-set conditioning. Now, why is it called conditioning? Because of this notion of assume something and then compute. That's conditioning on that node. Why is it called cut-set conditioning? Because it assumes that you can identify a set of nodes in the network that if you observe and delete the outgoing edges from, you render the network singly connected. So in this case, again, assume that we really have just 4 of these loops. Then the 4 nodes here are called a cut set for this network. And once more, the notion of a cut set is a graph theoretic concept. And there is a literature in graph theory that actually looks at optimizing the size of the cut set. I give you a graph and I say, find me the smallest cut set for that particular graph. We're good? That's cut set conditioning. Now, what's the problem? This is 80s, by the way. The problem is, for this particular network, what's the complexity of cut set conditioning? Assuming that you have enough of these loops, so you have n of them, right? You have n of these loops. What's the size of the cut set? In this case, big O of n, linear in the number of loops. You have to condition on one node in each loop to make this singly connected. Correct? So in this particular case, cut-set conditioning run exponential in the number of loops. What can you do with variable elimination or the joint tree algorithm? You didn't do yet a homework on joint trees, but if you start playing with joint trees a little bit, you look at this guy and you immediately say, I can get a joint tree for this guy whose width is 3. Basically what you need to do is, for every loop, you clamp it into 1, and you can actually easily construct a joint tree for this guy whose width is 3. Now, again, because we just covered joint tree, may not be immediate to you, but once you play with them a little bit, you will see it. So what does that mean? Joint tree algorithm run in linear time on this guy, because I can get you a joint tree whose width is 3, and cut-set conditioning is exponential. And that's pretty bad. That's a big difference between them. So since that observation was made in the 80s, there was an attempt to try to save conditioning. And can we use the conditioning concept to do inference in a way or in a complexity that's competitive with joint tree? And from that time up until around 2000, many attempts, I was involved in those, and we couldn't get it done until 2000, where The algorithm that I'm going to show you next, called recursive conditioning, not cut-set conditioning, did that. And not only it did that, but it came with another nice surprise. It matched the computational complexity of the joint tree algorithm, but in a very simple and nice way. It allowed you to trade time with space. Meaning, you tell me, I don't have space even to do separators or tree width. I have that much space. I'll tell you, I will run. I can run under any amount of space you have, but I will take more time. And I will characterize to you the amount of time I will take. Right? You'll see that in a little bit. Right? Recursive conditioning. This was done here. I actually introduced this algorithm around 2000. Here's how it works. And before I tell you how it works, look at the main insight. The main insight is this. What does cut-set conditioning do? It conditions on nodes for the purpose of reaching a polytree. That's what it tries to do. The main insight was, no, that's not the only way we can capitalize on conditioning. We can actually condition to decompose. And I'll tell you what that means now. Right? Here it is. Same concept, Bayesian network, I want to do inference on it. Let's say we're just doing the simplest thing of computing the probability of evidence. Someone comes and says, here's my evidence, these colored nodes, right? And, well, look what happens here. I prune the network, got disconnected. That's nice, actually. What does that mean? If I want to compute the probability of evidence on this network, now I have decomposed it into two different computations. I can compute the probability of evidence here. Let's call it left probability. I can compute it there, and what do I do with the result? Just multiply them, right? That's pretty good from a computational point of view. But again, I lucked out because of that particular evidence. What if I don't have that evidence? I can basically use the same technique in the sense that I look at that variable gas and I say, how many values does it have? In this case, 2. Well, assume the first, right, which is yellow. And then decompose, compute left, compute right, multiply. Now look at the other assumption, pink. Now it allows me to decompose, compute left, compute right, multiply. What do I do with these two numbers? I just add them, right? This is case analysis. We're doing case analysis here. Done. And you say, wow, that looks good. I took a big guy and I split it into 4 little pieces. How do I handle each piece? How do I do the computation with respect to each piece? Recursively, using the same guy, same process. Pick another node that if I fix the value of, I can decompose and repeat. Okay, this is much simpler than anything else we've looked at. Decomposition and case analysis can answer any query. The question is, you will have choices at some points. And what do I do with these choices? What do I mean by that? Here's the network. We picked that particular variable yellow and did case analysis on it. But you could have picked this other variable, this other yellow, right? In this case, I did this guy, and here I did that guy. Both are fine. The question is, if I do this versus that, which one ends up doing less work at the end? Now you're expert on the game. We've seen it in variable elimination. I need a variable elimination order. We've seen it in the joint tree algorithm. What do I need? An elimination tree. Here, we're going to introduce yet another device that once I give you, I guide you through the process. And guess what? What will that device have? It will have a notion of width. And the width of that device will determine the complexity of this guy, and then we're going to tie all notions of width. But it gets a little bit interesting here. Here's the device. It's also very simple to explain. It's called a decomposition tree or a D tree. Stare at it. This is the device for this particular network. So I have this Bayesian network at the top, A, B, C, D, E. And I'm telling you to guide you through this process of recursive conditioning. I'm equipping you with a D tree. So the D tree is nothing but a binary tree, the leaves of which are, what are the leaves? The families of the Bayesian network, correct? So if you look at this guy here, that's just A. Look at this guy, that's the family B given A, C, and so on, right? And this guy is the family. Very simple. Any binary tree will do. Let's use this to do run recursive conditioning. What are you going to do? Look at the root node. What is B? If you look at the variables that appear in this subtree, and you look at the variables that appear in that subtree, you take their intersection, it's B. It's the variable that's common between left and right. The family is on the left and the family is on the right. Okay? That's called the cut set for that particular node. What happens if I condition on that cut set? Look what happens. Since that cut set happened to be the intersection of variables on the left and the right, you are guaranteed, if you set the value of these variables, you will be decomposing the network into two pieces. Not only did I decompose the network into two pieces, I already have a D3 for this subnetwork, and I already have a D3 for that subnetwork. You guys see it? So look what the algorithm will do. Suppose I have this evidence E. I want to compute the probability of that evidence. I computed the cut set of the root. Case analysis. Yellow. Split. Recursive call on the left. Recursive call on the right. Probability, probability. What do I do with these two guys? Multiply. Second case, ping. Split. Recursive call. Recursive call. Multiply. Add. Done. Pretty nice. Very simple. Right? Now, look what happened here. I don't know if you realize this. What's the space complexity of this guy? What space did I use here? Nothing. The only space I need here is to store the D3, the families, and the stack for the recursive calls. I didn't store anything. It's linear. This is linear space complexity. Okay, that's already pretty interesting, because the joint tree algorithm was not linear. The space complexity is in the tree width. Right? This is linear. Now you're going to say, wait a minute. What about time for this guy? Let's do it together. And here where it gets interesting. But I can tell you right now, we will characterize the time complexity of this guy, which is linear. And then you're going to say, yeah, but that's worse. The time complexity will end up being worse than we did for joint tree. And then you're going to say, but can we do it better? And then I'll tell you, yes, but we have to start using space. And here's the final reward of all of this. If you use enough space, you will make it match the joint tree. But you don't have to use that much space. You can use any amount of space you want, and I'll give you a whole spectrum of time complexities. Right? That's going to be the reward of this algorithm. So let's do it together. Look at this guy. Question. How many times will this node be called recursively? The C, the one labeled with C. How many times will it be called recursively by this algorithm? Twice. Because I'm going to call this under B yellow and B pink, right? So it will be called twice, depending on the different states of that. You guys see this? How many times will this node be called recursively? How many times? 4 times, depending on the state of B and C. You guys see that? And so on. This guy will be called 8 times, depending on the states of B, C, D. You see that? Okay. Those sets that I just marked, we're going to call them the ancestral cut sets. So you pick a node in the tree like this guy, and I say, what is the ancestral cut set? You look at the guys above and take the union. Because what's the relevant of the ancestral cut set? I will call this node once for every instantiation of that. Okay. So if I can bound the size of the ancestral cut set, I can actually give you a bound on the time complexity of this guy. Why? Because each node will be called exponential in the size of its ancestral cut set, correct? I basically multiply by the number of nodes and, okay. Well, if you go to which chapter? 9, you find this result. It's a nice chapter. It's given a DAG with n nodes and an elimination order of width W. Look what we can do. We can construct a D3 in n log n with the following properties. Its height is log n, that's balanced. It has a cut set width no greater than W plus 1. each cut set is this. What does that tell you about the biggest ancestral cut set? Must be W log n. So remember, that's the height, log n. Ancestral cut set, I get it by unioning a bunch of cut sets. And what's the complexity then of this algorithm we just discussed? Is linear in the number of nodes, exponential in W log n. You guys see that? Compare it to the time complexity of the joint tree algorithm. What's the difference? Compare it to the time complexity of the joint tree algorithm. What's the difference? The log n. That's the penalty we incurred for using linear space. We're good so far? Okay, now we're going to get rid of this guy, and you're going to help me get rid of it. You're going to make the observation that says, this is why we're wasting time. And then you say, and then I'll tell you, how can we not waste time? Say, do this. And then we'll find out that, yeah, but to do that, I have to use space. Just a second. But let me give you some numbers to put this in perspective. Remember cut-set conditioning? Cut-set conditioning also used linear space, because when we were doing the iterations, we didn't have to save. But it was exponential in the size of the cut set. Okay? Let's look at some numbers here. These are networks from the literature, Bayesian networks. And I'm looking at the elimination order with, if I use joint tree, what do I do? What am I going to be exponential in? If I use the cut set conditioning, what am I exponential in? And if I use what I just told you, what I will be exponential in. Now, you're going to say, wait a minute, why is the width 21.3? The width should be an integer, because these networks have multi-valued variables. So we normalized, right? You give me a cluster that has 3 variables. One of them could have 4 variables, another 2 variables. We take the number of instantiation and log 2 to pretend what would be the size of the cluster if every variable was binary. Otherwise, it doesn't make sense to compare. Look what happens. The best is the width, right? This is what's happening. Loop cut set is pretty bad, right? Here's a network where the best we could do is to find that many. And here's the guy we just described. It sits in between. It's better than loop cut set, but not as good as that guy, right? Which is what you'd expect. Okay, now, there is a method for constructing, as you can imagine. You give me an elimination order, then you can construct a D tree from it with certain properties. I'm going to skip it. It's in your chapter 9, and I'll give you the slides. It's a nice animation. If we have time at the end, I'll come back to it. But basically, it shows you how to walk through an elimination order. It's very, very simple and nice. And you get a particular elimination D tree with the guarantee that the cut set in each one of these nodes no greater than W plus 1. There are more guarantees we're going to get to later. Now we're going to see why are we getting worse time complexity than joint tree, and how can we fix that? And you're going to help me. I'm going to show you this example. Look what's going on here. I'm running inference using this D tree, right? The cut set here is A. Cut set here is B, C. Now, as we already alluded to, this particular node that has A, B, C attached to it will be called 8 times recursively, correct? Once for each instantiation of A, B, C. Now, here's where the suboptimality is. And I will give you a hint by drawing this. This is your hint. What I did is I took the 8 instantiations of ABC and I colored them and I split them into 2 parts. That's your hint. You look at this and say, aha, that's why you're doing too much work. Where is the suboptimality? That particular node is called 8 different times, once for each of the colorings. Where did we miss? Look at this node here. When I get to this, I fixed A, B, C, correct? Look below this node. Which one of these variables appear? Just see. The states of AB do not matter. So if you look at the 8 instantiation, you can split them into 2 groups depending on the color of C, right? All of these guys will return the same answer. All of these guys will return the same answer. You guys see that? What I'm doing now is, even though these guys give me the same answer, 4 of them, I'm running this thing 4 times. And similarly, these guys here all give me the same answer. I'm still doing 4 runs. That's where I'm losing time. You guys see that? How do I fix it? I cache. Right? I cache. I look at this node and I say, wait a minute. The only thing that matters is the state of C, so let's put a cache attached to that node, which is indexed by the state of C. Correct? When you get to this node and solve it, see what was the value of C and enter it into that cache. So later when you get to this node again, see if I handled that particular value of C. If I did, just look it up from the cache. But now what am I doing? Using these caches. That's space. You guys see that? Now let's see what does that mean in terms of space. So we had the notion of a cut set attached to a node. Now we need to know, we have the new notion called the context. What is the context? The context, think of it practically as the variables that I need to use to index the cache. But the formal definition is you take the A cut set intersection the variables. So at this node, ABC is the ancestral cut set, and the variables are these guys. I take their intersection, I get C. That's the definition of a context. So now we have 2 sets of nodes attached to a node in a D3, the cut set and the context. And by the way, someone mentioned separators. In fact, the context, you can look at things in a certain way, and this ends up being a joint tree, and those guys are the separators. Very good observation. Okay. Remember, I gave you a method for constructing D3s from elimination orders. By the way, what I just showed here is the context in this particular case. Going back, we talked about a method that you're given an elimination order of a certain width, will construct a D3 for you. We didn't show the details, but the guarantee was that every cut set will be smaller than W plus 1, right? That method will guarantee you that every context is also less than W plus 1. What does that mean? That means the space complexity will also be exponential in the width. So here are the contexts in this case, and this method guarantees that every context will be less than W plus 1. Right? So what's the total space used in this case? Linear in the number of nodes, exponential in the width. In fact, this method not only guarantees you that, it guarantees you the following. If you go to every node and combine the context and the cut set, take their union, right? That union is also less than W plus 1. And that happens to be, we call that the cluster. So that's what I did here. I took, let's go back. For every node, I took the cut set and the context and unioned them, and I got this. We call these clusters. The guarantee is also that these clusters, their size is going to be less than W plus 1 according to this method. So what this means is you give me an elimination order with W, I construct a D3 with certain properties that if I run recursive conditioning on with caching, I get the same space complexity of the joint tree algorithm. And in fact, you can make a simple argument and show that the time complexity will be also the same. So what happened here? What happened is I have 2 extremes now. I run in linear space, but I give you time complexity that's exponential in W log n, right? The other extreme is you cache. Then you run in time and space that's exponential in W. This is joint tree. The other guy is new. But here's where it gets interesting. You come and say, wait a minute, if I do full caching, how much do I have to save? We look at the context, their sizes, and I tell you that much. At this node, you need to save 64 numbers. At this node, you need to save 128, 512, right? You add these guys up and you say, okay, that's how much space you need. You come and say, I don't have that much space. I say, how much do you have? Say, well, I only have 64. I can store 64 numbers. I'll tell you, fine, I still can do it. Right? I'll save only as much as 64. Now, then here's the question is what? What is the question? How are you gonna use the 64? I will have to remember certain things and I have to not remember certain things, right? Okay, look, the beauty of this algorithm. You really have to look it up. Let's say you go and say, here's what I'm gonna do. I'm gonna do only 8 there. I'm gonna do 16 here and 8 and 32 there, right? That's what I'm gonna do. How good is this? Because someone says, no. Do 6 there and do this here and do there. The algorithm has a nice formula. You can look it up in your book. That will count for you the number of recursive calls for any caching scheme. It will tell you if you use this, here's how much time it will take. If you use this, this is how much time it will take. When you have that kind of a formula, what happens? Now you can play the following game. Optimizing cache allocation. So there's a secondary optimization problem here, is where you come and tell me, I only have that much space. Find me the best way to use it. Because you have a formula that can evaluate the quality of a certain cache allocation, now you can solve this other secondary optimization problem where you do the cache allocation to minimize the running time. In fact, your book has some algorithm for that. One of our graduate students actually came up with this algorithm. And it should be implemented in SAM-IAM, where you can do this any space inference. Once more, you can optimize the running time for a particular cache allocation scheme. So now you have basically a spectrum. This is what we talked about initially. You can use linear space, but you get that kind of time complexity. Or you can do full caching, and you get this time complexity. This is joint tree algorithm. But then you have a spectrum. You can go in terms of space from this to that, and then your time will go from this to that. Right? You can be anywhere in that process, and that's what we call any space inference. Now, let me stress one more thing here, which already was coming in bits and pieces. That is, we've talked about so far variable elimination algorithm, and those were driven by elimination orders, right, that have width. And then we talked about the joint tree algorithm, which was driven by a joint tree that has a certain width, correct? And then we talked about a D tree that has width. The width of the D tree is the size of its largest cluster minus 1. What is a cluster? It's the union of the cut set and the context of a node. In your chapter 9, there are width preserving methods that can take you from any one of these to the other. Right? You give me an elimination order, you say I want a joint tree, I'll give you 1. I want a D tree, I'll give you 1, and back and forth, all based on graph theoretic concept. This is basically what we want to say here. But since we already have about 6 minutes, let me go to the thing that I skipped because it's really fun and end with that, which is the method for constructing a D tree from a variable elimination order. And then we will leave it at that. You know, all of this fine animation, we have to make use of it. So the purpose of this is to show you how to construct a D tree for a Bayesian network from a variable elimination order while giving a guarantee. You start by simply laying out the families of the Bayesian network. Remember, what is a D tree? It's a binary tree over the families. So you start like this, and very simple. You go over the elimination order variable by variable. When you look at a variable, you ask yourself, what subtrees do I have? that mention that variable. I want to wire them up. That's it. So if you look at F, how many of these guys mention it? Only one guy, right? Look at the find animation. DF, I do nothing. Let's look at E. Where is that mentioned? Only in this guy, ABE. Also, I do nothing. Okay, it's boring so far. Then I look at A. How many mention A? Quite a bit. 4 of them. All right, let's see it again. Here they are. What do? I wire them up. In which way? Any way you want. Just make them into a binary tree. Here's one way. Good so far? And then I look at B. How many mention B? How many subtrees? 2 of them, right? This guy and that guy. Okay, in case you've missed it. What do? Only one way to wire them up. Here they are. Final thing is, again, C. It's mentioned only in one tree, do nothing. And then D, it's mentioned in 2 things, wire them up. Done. This guy, as I discussed earlier, is guaranteed. Every cut set is going to be less than W plus 1. The width of this order is 2. But let's say abstractly W. This construction method guarantees you that the width of every, or the size of every cut set is less than W plus 1. The size of every context is W plus 1. The size of every cluster is less than W plus 1. Very nice for something as simple as this, and that ties the 2 methods together. All right, folks. I guess this concludes our discussion of the elimination and the conditioning paradigm. I just want to say one last thing. In variable elimination, okay, I'm choking. Let's see if I can finish the next 30 seconds. In variable elimination, we talked about a multiplication and a summing out operation. There is an operation we didn't discuss called maxing out, similar to sum out, but instead of doing addition, you do max. If you use that max out operation, then you can use variable elimination to also compute map and MPE in an almost straightforward way, given what we did. And that's discussed in your book, so you can check it out. So we'll leave it at this, and I'll see you on Thursday. Thank you.